So again, as you recall, last time we talked about Poiseuille flow between two plates, and we talked about Poiseuille flow in a tube with a circular cross-section. And we came to some conclusions. We said that if we solve for this flow, this pressure-driven flow with a uniform dp/dz in a tube with a circular cross-section, so as drawn here, we're assuming that we have some tube that has a radius r, and we have a coordinate in this direction denoted by the lowercase script r. We have a z direction along the axis of this tube, and eta is our viscosity. So we showed that this was the velocity in the z direction of this flow. We've assumed unidirectional. This tube we've assumed infinitely long. Now if we integrated this expression from 0 to capital R, we came up with a mean velocity field, with the mean now denoted with this overbar. And it turns out that that mean is actually exactly 1/2 of the maximum velocity in this flow. It's given by -1/8 eta times dp/dz times r squared. And again, this was a reminder of how the key parameters influence this flow. If I make things more viscous, the velocity slows down. If I apply a bigger pressure gradient, things speed up. And my velocity is proportional to the radius squared. Compare again this with the Couette flow, where the average velocity was not a function of the radius or not a function of the distance between the two plates. And this is a reminder that as we make this r smaller and smaller and smaller, this flow is going to become less and less important as compared with surface-driven flows. Now this, if I then took dp/dz and wrote this as delta p over L, and if I took this mean velocity and I wrote it as a volumetric flux normalized by a cross-sectional area, we were able to rearrange that into this form, which is the Hagen-Poiseuille law. And again, this is meant to be reminiscent of Ohm's law from electrical circuits. When we put this in this form, this R sub h is what we call the hydraulic resistance. Again, in analogy with electrical circuits, because this resistance plays the exact same role in the equation. It follows the same series rules, the same parallel rules that electrical circuits play. And that hydraulic resistance can be written in this form. And you can see here the elements of this solution over here. We have the 8 eta from that denominator. We have the L from the denominator of this expression for the pressure gradient. We have this area from the denominator of the left-hand side. And as I've written it here, I've now written a general expression that is meant to describe not only channels of circular cross-section, but in fact a channel of any cross-section. And the key difference is that I've replaced this radius with a hydraulic radius. And our definition of this hydraulic radius is that it's given by 2 times the cross-sectional area divided by the wetted perimeter, so the perimeter of the outside of this channel. Now, if you work things out, if you take an area of pi r squared and you divide by a perimeter of 2 pi r, you'll see that if you have a circular cross-section, this hydraulic radius is exactly equal to the radius of that circular cross-section. So for a circular cross-section, everything works out perfectly. In fact, if we have any other cross-section, as we would typically expect to get if we were doing any sort of real microfab, or at least any sort of plasma-based etching microfab, we're not really going to have a circular cross-section. We'll have something that's more often square or trapezoidal or rectangular. We won't be able to define a radius. We'll have to use a hydraulic radius. And this expression, which before was an equality, now really just becomes an approximate equality. And as a rough rule of thumb, as long as your shape isn't too crazy, we expect that this approximate relation with this hydraulic radius to be good to within about 20% error. So if I have some device, this is now meant to be some wafer, some glass or silicon wafer that I'm etching. And I etch some design. I have some channels, and I have an inlet and an outlet. And then these things branch off and connect to each other in various ways. As long as I know what this shape is, as long as I can assume that these channels are reasonably long as compared to their radius, as long as I can approximate this hydraulic radius, I can now come up with a pretty good approximation of what the volumetric flow rate is in each channel. And because this is all a linear system, it doesn't require my solving any ordinary differential equations or partial differential equations. This allows me to take a system like this, and even if I make it much more complicated with lots of inlets and outlets and connections and different sizes and shapes and different depths, no matter how complicated I make this device, I can still come up with a solution quite straightforwardly because it's basically a bunch of linear equations. I can just put it in a matrix and invert it. So if I go and I make a microfluidic device, and I look at it from the top, I may have a shape that looks a little bit like this. These channels will have some characteristic width. If you do routine photolithographic fabrication, the characteristic size of these channels might range from about 5 microns all the way up to, I guess you could do maybe 5 millimeters. That varies a little bit based on the material that you're using. There will be a depth of these channels into the device, and that depth is basically a function of the etch process and the etch time. That can range from all the way from, say, 10 nanometers to about 100 microns. If you want to make this feature much smaller than 5 microns, that's definitely possible. In fact, it's routine. It just would be done with something other than photolithography. It might be done with e-beam lithography or a technique like that. When we have a device like this, we can think of all of these tubes as basically being hydraulic resistors. We can think of all the connections between the tubes as being nodes in an electrical circuit. And we can take a device that physically looks like this and recast it in terms of a circuit that looks like this. Again, recasting in the circuit allows us to take this linear relation, this Hagen-Poiseuille relation, and put that into a matrix form. So for example, if I have a device that looks like this, and this is the outlet, that's at an ambient pressure, and this is an inlet, and maybe I've connected this inlet to a pump. So I have a lab, I have a microfluidic device. It has an inlet and an outlet. I connect the inlet to a pump, and so I apply a pressure that's larger than atmospheric pressure here. I expect that to cause flow through these channels, and I want to come up with an estimate of what the magnitudes of those flows are. That is completely analogous to having an electrical circuit and applying a voltage at one inlet and having the other outlet connected to ground. So we can think of this system then as having some pressure at the inlet, some pressure at the outlet. There's a node here where these connect, and I can give that a pressure as well. I can say really that there are 3 different tubes that I want to consider. And so I can say that they each have flow rates. And these tubes all have geometric characteristics that will allow me to calculate a hydraulic resistance. Recall that from this equation up here for the hydraulic resistance, I need to know the fluid property, which is the viscosity, but other than that, I just need to know geometric parameters, the length, the cross-sectional area, and the hydraulic radius. And so this resistance, or this tube, can be thought of as a resistor with a hydraulic resistance of R sub H sub 1. This one I'll call R sub H sub 3, and this one I'll call R sub H sub 2. Now in this format then, I basically have some unknowns. I have a number of governing equations that will specify this. Again, they're all linear equations. And I can just put this together into a matrix. So if I know the geometry, I have these resistances which are known. Other than that, I have 6 unknowns. I have the pressure at these 3 different points, and I have the flow rates through these 3 different channels. And so I can think of my unknowns as P1, P2, and P3, and Q1, Q2, and Q3. To make this a well-defined problem, I have to say what the pressure is at the inlet and the outlet. So I can say that P1 and P2 are specified by the problem. And then beyond that, I have 6 unknowns. 2 of them are now known because I've said I specify them as boundary conditions. I need 4 more relations to complete this problem and basically make it a 6x6 set of linear equations. Now when I look at this, I have 3 different channels. In each of these channels, I can apply the Hagen-Poiseuille law. And so, for example, through this channel, I can say that the pressure drop is proportional to this flow rate times this resistance. Through this second channel, I can do the same. Through the third channel, I can do the same. So I have 6 unknowns. I specified 2 of them. And I use the Hagen-Poiseuille law to define 3 more. How can I get 1 more equation to complete the specification of this problem? This one is RH2. Thank you. So the question is, can I take these resistances and combine them in series and in parallel to solve this problem? So I can solve this problem by using series and parallel relations. But using those series and parallel relations is, in fact, it's basically just a shorthand way of doing everything that I'm doing. So that's important and correct, but not unique relative to what I'm doing here. I do need one extra separate bit of information. Yeah? And how shall I add the currents? Right. I've used the momentum equation to define the Hagen-Poiseuille law, but I haven't satisfied mass conservation. And so mass conservation in an incompressible fluid says that the volume that's going into a tube always comes out of that tube. And the volume that goes into a node always comes out of that node. So that means for each node, I can apply conservation of mass. And again, the analogy of this with electronic circuitry is Kirchoff's current law. Kirchoff's current law says that the current into a node always comes out of the node, or the sum of the currents is equal to 0. Equivalently here, the total sum of the mass into a node is equal to 0. So Q1 and Q2 are going into this node. Q3 is going out. And so I can say that Q1 plus Q2 is equal to Q3, or equivalently, Q1 plus Q2 minus Q3 is equal to 0. So now I have 6 different equations. I can say, for example, I need to specify the inlet and outlet pressures for this problem. So let's say I say that P1 is 1 atmosphere, and I say P0 is equal to 0 atmospheres. In this case, this is gauge pressure. So I have two equations that are specifying boundary conditions, three from the Hagen-Poiseuille law, which is conservation of momentum, and one from conservation of mass. Yeah?
What do you mean by P0 atmosphere?
So I am saying that I have this system in the lab frame. Oh, wait, I'm sorry. You're right. I'm using bad symbols. This shouldn't be P0, but rather P2. Thanks. So, of course, in a system that's small enough, one can simply take the linear equations and rearrange them and solve to get a solution. But as soon as the system gets reasonably large, we want to put this into a matrix form so that we can solve it through matrix inversion. In this case, we have 6 different parameters. And so our solution vector is basically P1, P2, P3, Q1, Q2, Q3. And we now want to write a matrix equation that describes these 6 equations. And that's relatively straightforward to do. I have my first equation says that P1 is equal to 1 atmosphere. And so as I've written this matrix here, I'm basically saying 1 times this pressure plus nothing else is equal to 1 atmosphere. I could do that for the other boundary condition. If I take my conservation of mass equation, my Q1 plus Q2 minus Q3, I have Q1 plus Q2 minus Q3. That's equal to 0. And then I have 3 different equations which are in this Hagen-Poiseuille form. The first one, for example, is P1 minus P3 is equal to, or P1 minus P3 minus RH1 times Q1. Equal to 0. And so on and so on. P3 minus P2. And once I have this set up, now all I need to do is invert this matrix, multiply it times this matrix, and that will give me my solution vector for these pressures and flows. Now, if you take this to MATLAB, and you calculate out all your resistances, and you put them here, you take these ones, you calculate all these things, it will not work. MATLAB will not be able to invert this matrix. Why might that happen? At least usually it can't invert the matrix. Yeah, Marie. So well, of course, it depends on how we define the units. And so certainly if we define inconsistent units, then we'll either get no answer or the wrong answer. What you say really does hit at the key problem. And the key problem is that if you use SI units like you've been taught, then you'll find that these hydraulic resistances are not going to be close to 1. In fact, they'll routinely be 8, 10, 18 orders of magnitude different from 1. And what that will do is that will make this matrix ill-conditioned. And so numerically, when MATLAB goes to invert it, it's going to be adding and subtracting 1 from 1 times 10 to the minus 14th. And then it's going to subtract 1 away. It's going to get all these problems. So from a mathematical standpoint, this is perfectly defined, and this is a trivial, straightforward matrix inversion. From the practical point of really doing it for a homework problem, the key thing you'll find is if you do this all in SI units, these numbers are way, way, way too small. And so you can fix that by using any consistent set of units that make that number reasonable. As long as it's within 6 orders of magnitude or so, MATLAB or Mathematical will be able to handle it. The way I do it is I do everything in units of microns instead of in meters. That basically cleans everything up. But other than that detail, this is now trivial. You type one line in MATLAB, this inverts it, you get your answer. And even though, I mean, I don't know what you all think, I find it kind of unwieldy to take these nice, clean, simple equations and write them in this awkward matrix formalism. But once you put everything in a matrix formalism, it doesn't matter if your system has 50 nodes or 500 nodes or 1,000 nodes. It's still a relatively straightforward thing to code up, a relatively straightforward thing for MATLAB or any other program to then invert. Now, this Hagen-Poiseuille law, which we're applying here, is only correct in a number of limits. We needed to have unidirectional flow. The tubes needed to be long. We needed to basically assume that the effects of the edges or of the nodes was relatively small. But oftentimes, this is a perfectly reasonable approximation in these microscale systems.